Hello everyone, Dr. Shane here. It's an early morning for me when I'm doing this one, but I'm ready to go, got the coffee. Um, this is our third major topic. Well, we're probably somewhere in week 3, who knows? We might even be at the beginning of week 4 with this topic. And this will likely be the last major topic before the first exam, so it's nice to kind of bring that sense of closure to this. Before you get started with this topic, you want to go and watch the first video from the week assignments and look at the demos, see what kind of hypotheses you can make, conclusions you can draw, and then post something on the discussion board. It's not really a discussion board, but what did you take away about intermolecular forces from those demos? So do that before you do any of this. If you need to stop this and go do that, that's fine. It's just a nice way to do it. This section is going to involve some synchronous instruction. The lectures that I'm doing here are just for the basics, and we'll need to do case studies in the mathematics in class. So plan on coming to class for this set of lessons. Okay. Also, I want to give you a preview of coming attractions. Whenever possible, it's important for me to become a student and to learn, and also to learn things that I think are important for you to know. And right now, I can't imagine anything more important to learn about, not all of it, of course, about this. I think by now you probably know what this is. This is a cartoon representation, a schematic, it's a good one, of the SARS-CoV-2 virus. So severe acute respiratory syndrome is what it causes. It's an airborne virus, so it gets in through your nasal passages and your lungs and causes some respiratory problems, but then cascades into all kinds of things that can go wrong. It's also, the CoV stands for coronavirus. That refers to the crown-like structure, corona means crown in Latin, of these spike proteins on the exterior surface. This is what gloms onto your cells and then allows the either DNA or RNA, in this case it's RNA, on the inside of the virus to get into your cells and replicate and cause all kinds of problems. This is not a virology course, so we're not going to go into it more than that. Something you've probably seen before is if you've had any biology before, especially any cell biology, this is a schematic of a cell membrane. And there's a lot we can learn about intermolecular forces here. So cell membrane is the classic phospholipid bilayer. So you've got these long chain molecules called lipids that line up with each other because they're non-polar. They aggregate in the middle. You've got this polar part on the outside, which then interacts with the water and prevents it from just falling apart in the middle of water, which is most of your body. Then you have very sophisticated things like these channels that allow sodium and potassium to go through. There's even cholesterol embedded in there. And then you have these things also embedded. You have other proteins, glycoproteins, and glycolipids. But again, it's not a cell biology course. The chemistry that we can learn about is this. At first glance, this may look like some sort of maybe this looks like a virus or some other biological organism. It's not. This is a synthetic structure, which I find amazing. It boggles my mind. This is called a lipid nanoparticle. And when you get a shot of the vaccine, hopefully very, very soon, this is what's being used to deliver the actual medicine, if you will. In this case, what's being delivered is a strand of messenger RNA that will then prompt your immune system to promote antibodies, to promote an immune response so that it recognizes SARS-CoV-2 and can take care of it. Because right now our immune systems aren't very good at that. So that's what we're trying to do with a vaccine. That's what all vaccines do. So the messenger RNA, if you want to see it on the middle of this picture, I think I might need to go to another color, is here in the middle on this blow up part. And all this other stuff around it is meant to deliver it to your system, to get through your bloodstream and get into your cells. So this little legend is really handy. So there's the thing that's actually going to promote the immune response, the messenger RNA. So what's the deal with A through D? Why are these necessary? So you've got this stringy stuff on the outside called PEG, which stands for polyethylene glycol, a synthetic molecule. Then you've got some lipids, and then you've got cholesterol. So all of these are being used to deliver this to your system. Why does that work? And I'm probably going to ask you to explain that somewhere along the way. An exam, a quiz, is what's the role of these four molecules? So if you want to do that right away, and how do the principles that you're about to learn apply to that? And let's see, I think that's it. I'm not sure I put it on the slide there, but there's a really interesting video that I watched from Carnegie Mellon about lipid nanoparticles. You can actually just type that into a search engine, lipid nanoparticles, Carnegie Mellon, and you'll come across a researcher's website. Her name is Katie Whitehead. She's one that's pioneered this technology. It's amazing. She does amazing work, and you can take a look at that. She's not the only one. There's some others in Germany and at the Massachusetts Institute of Technology. But let's get started with the basics. So we're at Roman numeral 3, fine. Subset A, I have to review some things real quick. States of matter, solids, liquids, gases, and the phase changes. We can learn a little bit about intermolecular or interparticle interactions from that. So set this up, and also be sure that you have your electronegativities on your periodic table. You don't have to do the whole periodic table, just these. The metals and maybe some of the metalloids, like fluorine is 4.0, chlorine's, what is that, 3.0, hard to read. Oxygen, so make sure those are transferred to your periodic table. We'll need those, so stop the video and do all of that if you need to. Okay, states of matter and phase changes. All right, so just basic definitions. This is real quick. This is like middle school physical science. Solid, liquid, gas. Just to remind yourself, let's use 6 blobs, generic blobs. So solid retains its shape and volume. When it goes to a liquid, it takes the shape of the container. And when it goes to a gas, it takes up the whole container. And you get the collisions, which is gas pressure, a lot of kinetic energy going on here. And solid to a liquid, we call that melting. If I make mistakes, just correct them. So solid to a liquid is melting. Going from a liquid to a gas is one of a couple of things. It's either boiling or evaporation. The intro video that I showed goes to that distinction. I'm going to reiterate the definition of boiling point because it's so important. Boiling point is the temperature at which the vapor pressure of the liquid, so the vapor pressure pushing up, is equivalent to the atmospheric pressure pushing down. If something has a high boiling point, it's hard to boil it. Lots of intermolecular forces, strong intermolecular forces. Low boiling point, weak intermolecular forces. And we'll go more into it than that. And the reverse direction, going from a gas to a liquid, is condensation. Going from a liquid to a solid is freezing, sometimes called fusion, not to be confused with nuclear fusion. And you know that some substances, dry ice, iodine, skip the liquid state under standard conditions, like room conditions, if you will, and that's called sublimation. And the reverse, which is not often put into textbooks, going from a gas to a solid, is called deposition. And when you go from a solid to a liquid to a gas, those are endothermic processes. They have to absorb energy. And those are entropic processes. They create more disorder. Well, then the reverse has to be true, going the other direction. Those are exothermic processes and entropic processes. They create more order. Okay, basics. So we can learn a lot about solids, liquids, gases, just definitions and intermolecular forces based on that. We'll do that in class. Okay, the major parts of the notes are right here, so I'm just going to give these to you. Just write these down, and I'll do examples of each on the next set of slides. While you're doing that, if you wish, or if you want to stop the video and then listen to it, this is just another interesting picture. So there's a lot of gas pipelines that are being built in Pennsylvania, not just Pennsylvania, but all over the country. And they're fairly controversial as they're being put through land, and some people don't want them there. There's been a lot of news in the Dakotas about some Native American tribes stopping the building of pipelines, actually, but we're not getting into the politics of it. Basically, what's going on there is you're taking natural gas, about 80% of which is this molecule, methane. You're putting it in a pipeline, and it goes along the Pennsylvania Turnpike, for example, if you've seen it there, And it's going to these facilities on the coast. I think this picture is actually from near Philadelphia. And under high pressure, you compress it from a gas into a liquid. That's called liquid natural gas, LNG. I still find it pretty amazing that we take natural gas, compress it to a liquid, and then ship it to other countries. That just blows my mind that we do that. So that's another example. And natural gas is really hard to turn into a liquid because the intermolecular forces are so weak. So you have to really cool it down and compress it to force them to go from a gas to a liquid. Very difficult to do. Okay, so there's your examples. Fine. I'm just going to briefly overview these. Dipole-dipole, ion-dipole, and London dispersion forces. So, well, first off, dipole-dipole interactions are going to occur with molecules that have a dipole. What do we call those? Well, we call those polar molecules. I may do more of these in class. So if the molecule is polar or it has a really polar bond in it, it'll interact with other ones. So let's just do the classic, the one we always do, is water. If you need to review this, please do so. Water's bent. Oxygen has a higher electronegativity than hydrogen. So the electrons in the covalent bonds get drawn towards oxygen. Oxygen then has a partial negative charge, leaving behind a partial positive charge on the hydrogens. That's called a dipole, a plus-minus separation, a permanent plus-minus separation. It's a permanent dipole. I say it with such emphasis to distinguish it from something later. So if you have a bunch of water molecules, nothing says you can't change that. So the negative part of one will attract the positive part of another one. And that'll happen in bulk in, say, a glass of water or in your body, something like that. And okay, let's just use that as an example. We could take tons of examples there. And when the separation is particularly strong, when you have hydrogen bonded to a particularly electronegative element like oxygen, fluorine, chlorine, that's a specific type of dipole-dipole interaction called hydrogen bonding. So hydrogen bonding is a subset of dipole-dipole interactions. So that's when hydrogen is bonded to a particularly electronegative element, you will see this. Fine. Ion dipole is exactly like it says. It's the attraction of an ion, shocking, cation or anion, to a molecule that has a dipole, so a polar molecule. All right, well, let's just do, I don't know. I guess I'm just keeping these on like middle school level examples. So like sodium chloride when it dissolves in water, and we write the AQ subscript. Well, what's going on? Well, chlorine is going to interact with the positive end of water. It's not hydrogen bonding. It's ion, so it's ion dipole. And then sodium is going to interact with the negative end. These are just about the easiest examples I could discuss. So ion dipole. Okay. I need some space for this next one. So dipole, dipole, ion dipole. Well, what if there aren't any ions? What if there isn't a dipole? Something's got to hold it together. Well, the example I'm going to use is even more bizarre. I don't know if you've heard of liquid nitrogen, of course. I guess I could use that as an example. But liquid helium is a more stark example. Helium doesn't even react. Helium is one of the most unreactive substances out there. In fact, I don't think there's any known chemical compounds that contain helium in them. So you can actually make liquid helium. It's a pretty important substance, actually, and there's some concern that we may be having a worldwide shortage of helium that we can make liquefy. Liquid helium is used to cool superconducting magnets that are used in MRIs. So if you've ever had your body imaged for an injury or something like that, an MRI, you need liquid helium for the magnet. We have an instrument in our basement, which is a basically molecular MRI called an NMR machine, where we actually have to put liquid helium in it. But if it's so unreactive, it's an atom, so it has no dipole. What holds it together? And it doesn't hold it together very well because this is a very weak intermolecular force. So I'm going to do this sort of dumb picture. So helium is an atom. So we could I'm just going to take two helium atoms, and we could go through the electrons because it's only 1s2. So you're just going to have two electrons in this spherical cloud, right? And the nucleus is somewhere here in the middle. So that's when it's a gas. It's far apart, they're not interacting with one another. But let's say you go through the process of cooling down the liquid helium, you compress it, and you bring them closer together, because that's what you're doing on a molecular level. You're taking it from a gas into a liquid, but you're forcing it. Well, what happens when you do that? When you take two atoms, or molecules, it doesn't matter, I'm just using the most simple example, and you force them into the same space. Well, remember what all these letters mean. These are electrons. These are clouds of electron density. So when they get forced together, they're negative charge. They're going to repel one another. So what happens, and I'm exaggerating this greatly, those electrons are going to repel one another and push the electron clouds away. This is a total exaggeration. Well, what does that do? Well, that puts more negative charge on one side than the other. So this is a partial negative charge here, leaving behind a partial positive charge. But these are temporary, what are called induced, because they're created. They're not permanent like dipoles in a polar molecule. They are temporary induced dipoles. They're created by the fact that they're interacting with another molecule. So here's what happens with London dispersion forces, sometimes just called dispersion forces. London, because that's the town where they were discovered. Not London, Ohio, London, England. That was a bad joke. So what happens when you have something that's nonpolar is you constantly have, actually any molecules, you constantly have this cycling of temporary induced dipoles forming and reforming, and that's the force that holds them together. It's very, very weak. That's all I think I want to say about it now. And let's move on. Oh, I have some pictures here, just because they're harder to draw. So methane, so that's CH4. We could draw the structure for that. It's tetrahedral. It's nonpolar. The bonds aren't very polar at all, and it's symmetric, so it's nonpolar. So this picture here is actually what's called an electron density map. So why do we have liquid natural gas? Well, when you bring all these molecules together, they distort each other's electron clouds, electron density. And the basic idea for methane or helium or any nonpolar molecule is this. I forget where I got this picture, but this is trying to show you the temporary nature of these induced dipoles, just using a generic molecule blob. So you form temporary dipoles, plus minus, and then throughout the whole structure, that's what holds them together, and it's pretty weak. Oh yeah, some other electron density maps. We'll probably talk about these in class. Ethanol is a polar molecule, so you do have a polar bond up here. So this would be, you would get dipole-dipole interactions with ethanol, or with ethanol and water, and we'll probably draw that in class. Hexane has a symmetric electron density. I think I used cyclohexane in the demo. So hexane is going to be nonpolar, which will imply London dispersion forces that will hold that together. Ethanol is polar, so you're going to get dipole-dipole. We'll do more of these in class and draw them out. Oh yeah, oil and water. So here's some general takeaways that you want, and I'm going to just stop the video here. I don't think I'm going to put any more examples. I'll save this for class. So some generalizations about intermolecular forces. I've already said it a bunch of times. Probably the biggest takeaway is that dipole-dipole is stronger than London dispersion. It's a lot stronger. And hydrogen bonding is the strongest of all. Well, ion dipole are pretty strong, but they're not as important for what we do in this class. Okay, so if you have nonpolar molecules, basically London dispersion forces are your only bet. There are also other combinations. If you have polar molecules, well, when you bring them close together, they induce dipoles as well. I mean, that always happens, actually. London dispersion forces always happen in all molecules once they approach one another. So you can induce dipoles in anything, with dipoles, with ions. And then there are other factors, which I think we'll save. How big the molecule is. What's its shape? Saturated and unsaturated fats are a great example here. And then we can start to be able to understand something like this. Why do oil and water not mix? And I think that's where I'm going to leave it. Let me see what else I have here.